Okay. Okay, let's make sure everyone's we get excellent health there. Permanent quality. Okay. Guess we'll go live. Agilex 7, not Agilex S5. Okay, let's go ahead and say hello. Be starting in a few minutes. I don't have any. I'm not going to have the chat on stream this time. I'm going to try to keep track of the chats and not have it overlap the screen. Okay. Mute my laptop. That's going to get awkward. Okay. Is audio good? Is video good? We all good? Okay. It's 2 o'clock, so let's get started. Welcome to FPGA Zealot. We have the Agilex 7, the Altera Agilex 7 that we're going to go over today, and we're going to try to do some simple examples through the Cordis vendor tools. So the agenda, we're going to talk about the company, the FPGA, and then we're going to talk about the dev board and go through some of the built-in tests, and then do a few different Cordis projects to demonstrate the hardware. This is an Altera sponsored live stream. I am not employed by Altera, and I do not offer any official support for their products. The content for this channel is my own for information purpose only, and they are my opinion. So for socials, we are streaming on Twitch, YouTube, and LinkedIn Live today. But feel free to watch the recordings later on YouTube or Twitch, or to follow on X, where I probably have the most little small updates about projects that are going on. And feel free to use the chat in LinkedIn, Twitch, or YouTube. Go ahead and, if you want to, talk about your experience with FPGAs, what products you use, what applications you go for. Feel free to share some of your experience while we get started here. So first, let's go ahead and talk about Altera. So Altera is what used to be known as the Intel Programmable Solutions Group. Earlier this year, I think about February, they announced that they were being kind of spun off as a new company, Altera, which has the same name of the FPGA company that Intel acquired quite a few years ago. So it's gone from Altera to Intel Programmable Solution Groups, probably whatever Intel added to that. Now it's spinning off again to Altera. They have several new products, so Agilex 9, 7. The 5 is coming out later this year, and Agilex 3 is probably sometime next year. We're going to look at the Agilex 7, because that's what Altera was able to send me. So we're going to look at the Agilex 7 FPGA. It's going to be the I series. And mostly the F, I, and M series are just kind of more incremental improvements to the Agilex 7. We're going from 500 to 2 million LUTs up to 4 million LUTs, going from 58 gig transceivers to 116 gig transceivers, PCI 4 to PCI 5, DDR4 to DDR5, and such. So we're slowly incrementing improvements here. For this today, we're going to go look at the I series, which is mostly dealing with high-speed transceivers, including PAM-form transceivers, as well as PCIe. The dev board that I have does not have any PCIe 5. It's mostly looking at PCI 4. So this is the hardware. You can see it up in the the upright corner above me. There's a little picture, a little live stream of the board. We'll look at it more in a second. We have the Agilex 7 transceiver SoC development kit. This has 4 F-tiles. So an F-tile is their main transceiver bank for their FPGA. There's also a P-tile, and that has the PCIe Gen 5. And let's see, anything else? I guess we can look at the block diagram. The block diagram is probably the best way to introduce this hardware. And Kevin, I look forward to hearing about your experience in redoing some of these hopefully basic Cordis projects. So this board actually has 3 FPGAs on it. It has 2 smaller Max 10 FPGAs. One Max 10 is the power system, and it's mostly handling the power and the JTAG interfaces. Then we have the system Max 10. This is handling the configuration of the Agilex 7. It's handling the clock PLLs and some other user push buttons, dip switches, and LEDs, as well as the QSPI flash that holds the non-volatile configuration for the Agilex 7. So the Agilex 7, we have we have 8 general purpose IO banks. So we can use these for basic IO for like the FMC. These are the basic IO on the FMCs. We can also use this for kind of high-speed single-point I/O, which is going to our DDR4 SODIMM and our DDR4 component memory. We also have a specific bank for the HPS, which goes to our little daughter card that we'll show you in a second. That has SD card, Ethernet, USB, UART, stuff like that. Then we have our 4 F-tiles. The F-tiles on the right, those are going to your FMCs. This is for FMC pluses. They have 16 lanes, which is great. You can use a lot of the FMCs provide you a way to expand to your application. So you find FMC daughter card for PCIe, ADC, DAC, Ethernet, a lot of different interfaces you can find for FMC plus. On the left side, we mostly have QSFP, which are just high-speed Ethernet going up to 100 gig, 400 gig. I think the MXPs are the PAM4 connections, which are really cool. They do like 4 levels instead of 2 levels. So you got 0, 1, 2, 3 rather than 0 and 1. We also have a USB-C plus, USB 3. It's only 1 lane. No, wait. Oh, you can do DisplayPort over it as well? Okay, so that would be interesting. I wonder if there's got any examples of USB-C with the DisplayPort. That would be really cool to see those examples. This other F-tile goes to an MCIO connector, which is kind of like a data center-based PCIe cable. Hopefully we can look at that maybe in future weeks or streams or posts. But this is the block diagram. Now let's go jump over to the actual hardware and see what this looks like. I gotta stand up. So, okay. Might be hard to hear me. At least I can hear myself, so hopefully you can hear me. Okay. So we have the development board on a ESD mat, and we're going to put on a ESD bracelet to get to wristband to do common ground. But so we have the main Agilex 7 in the middle of the heatsink. We have the USB JTAG over here with the power base Max 10, the power regulators right here, the power cable right here. Let's see what's to walk to next. We do the hard processing system expansion card with SD card, Ethernet, USB, UART. We have the DDR modules, 72 bits wide for ECC. We have one FMC here, another FMC here with loopback, QSFP ports. What do they call these ports? These ports, they call them MXPs. So XP ports, USB port, MCIO port, DDR4, a bunch of LED, push buttons, dip switches, non-volatile memory for configuration. I think that's about it. So there's a lot of different things you can do on this hardware. So a lot of different options. Oh, also the SDIO and the USB. Oh, over here, all these SMA cables are for like custom clock refs. Okay. So if you're looking for a free Cordis license for Agilex, I would look at the Agilex 5. So the new Cordis Pro 24.2 supports a free license for the Agilex 5 hardware. And there's like, I don't know, like 5+ third parties that are going to have some dev boards coming out in the next few months. So Arrow, I think we have Arrow, Trex. There's a lot of other companies where we'll see some Agilex 5 hardware with the free license. Okay. So we're going to go ahead and pop open the user guide and talk through the built-in test. So the user guide provides basic self-test, some information on the power and the clocks, and some configuration information. But if you want to see some more examples, you're going to have to look at the examples course provides, and potentially retargeting to this hardware. Okay, so there's 4 versions. I got the most recent version with the VB, and this is just a note when we make the projects. We'll target that hardware. So this comes with a picture of it, a board test. So we're going to go ahead and open this up and walk through it. I gotta go turn the hardware on real quick. So we're going to turn the hardware on and walk through this board test example. Ooh. Okay, we're going to come run this. Okay, so this is going to be the background GUI for this. Okay, if you're new to the stream, welcome. This is the FPGA Zealot. We're looking at the Agilex 7 from Altera. This is a sponsored stream. You can find us on LinkedIn, Live, YouTube, and Twitch. Feel free to say something in the comments. Drop some questions or comments about your FPGA experience, your applications you want to use, soft processes, RISC-V. Feel free to add anything to the comments and we can address it as we go through the stream. So here's the board test. We're going to go through the clock and power real quick. So we have 4 PLLs. I mean, there's this 5th PLL, but what is it saying? It wants us to use a different menu for that one. But we have these other 4 PLLs, which we can go ahead and change the clocks to anything we want, which is really useful. And these clocks go to the normal IO banks, the F tile, so you can target a lot of different line rates that you want to use for your system. And then we have some basic power, where we can look at all the power rails within the system. It should populate here. Let me see if I hit reset. It should populate. Okay, so we have a voltage, current, and power, which is great. You can load in your custom SOF through this application, turn on the power monitor, and monitor how your custom application power usage is running. And there's other power usage tools, I assume, through Cordis. Okay, so let's go ahead and look at the basic GPIO example that comes with the hardware. And you can see the background, the system console, I believe what it's called, is programming the board and connecting to the various JTAG master management systems on the Max 10 and Agilex 7 FPGA. Okay. Coming up. Okay, so hard to see. So we can change out the LEDs. Yeah, we can turn the LEDs on and off right here. And we have the user dip switches. I might go change one. And then we have the push buttons. Okay. I'm going to go over and change out some dip switches. Right, so I'll leave this on so you can see. You see thing. Okay, so dip switch 1. Okay, you can see, yeah, with the dip switch. And here is PD with that 1. Okay, so those are kind of the basic I/O that are available. Next, we're going to load the FMCB with the loopback to see what we can get on the FMC system or test. Cool. Looks like the LinkedIn Live is doing well. This is my first time streaming on the system. My tool is kind of built for, like, Twitch or YouTube. I had to play around with the settings to get LinkedIn Live, but it seems to be going well. We got good stream health. We got good interaction. I wonder if LinkedIn Live records the video. I'm gonna check that out. Oh, in the description on YouTube and LinkedIn Live, there are links for the hardware and the examples and tutorials we're going to go through. If you have any questions about the source, feel free to download those files and to go through the system. So yeah, let me for the Max 10, if you download the files, it comes with a POF for programming it. So if you screw it up, you can reprogram it with a POF provided by the system. But this would be specific for this hardware. I do not know of any generic POF file that would fulfill that or source for that. Okay, so let's go ahead and start the loopback test with Perps 31. So we're going to hit details here, and we can see that the PLL has locked and the pattern sync has locked. So we have all 16 lanes operating correctly. Now we can look at the data rate and see that each lane is operating at a little below 26 gigabits per second. And this is not I assume you can push this faster, but depending upon your system and the burst rate you want, this example is at 25.7 gigabits per second. We can also introduce failures and look at how those failures affect the burst rate. It'd be really cool if I had like a really long FMC cable and connected FMC A to FMC B and see if we could see any errors through a longer cable that doesn't have the best signal integrity. Okay, so next we're gonna do the DDR test. I don't have any other hardware to demonstrate the other examples. Okay, let's get the DDR going. So, Manote123 on YouTube, you asked, what type of field would the Agilex family be targeted to? So, the Agilex 7 is pretty high end. You're dealing mostly with like transceivers. This would be mostly Ethernet, so you're probably dealing with like some type of custom switch in a data center. PCIe offers a few different options, mostly doing like hardware acceleration. This acceleration can be for video, AI, or any other type of application you want to do hardware acceleration on, mostly probably at the data center level. And then there's a really cool example I want to look at. They have a smart PCI switch. So you can actually implement a PCI switch into the Agilex 7. I wish I had the hardware to test that out, but that'd be a really cool example to look at. I don't think of any other hardware that comes with a PCI switch example. It's probably really unique for the Agilex 7. Okay, so back to the DDR. We can see it's running at 2666. That's pretty standard for, I would say, FPGA DDR4. I do know that the M series will go to DDR5, so you can probably achieve much higher speeds. I don't know what the top speed for this hardware is, and you might be able to get different speeds for the components level or different speeds with the DIMM level. Okay, so we can insert errors when it gets back to the air. There we go. We can change the size and do walking zeros. We can start. Small size makes this a lot slower. Okay, and we can just introduce errors real quick. So those are the basic examples I can run right now. But there's one more example we can run. So we're gonna go walk through that real quick. Close this out. I'm gonna open this up and turn off the hardware real quick. Okay. So rocket boards, which is being moved to a new location, and when we get to a new location, we can talk new website. I think it's going to GitHub, with a GitHub hosted website. We can post that later in an update somewhere. So this is Linux, a form of embedded Linux running on the hard processing system for this specific development board. And we're going to run through the examples, but if you go to this website, you can get the source. I just want to say that this version of the SD card and image will work for this version of the hardware. That's what's shipped with, apparently. So we're going to basically look at, where is it? There's a little website right here. So you can host a little website, or a little website is hosted when you boot this Linux. So we're going to boot the Linux image and look at this. Okay, so let's go and talk about what we need to do to get this booted up. Okay. So the system, make sure I can talk clearly from here. So here's the HPS expansion board is right here, and it comes with a SD card. You're going to have to configure the SD card with the appropriate image. Then you have your serial connection and your Ethernet that we're going to need to do this example. Also, switch 9 right here is the boot mode, and you got to go from JTAG to QSPI to get this up and running. You're on QSPI already. So I'm going to get the UART window up and running so we can look at this. Let me clear it out so you can see it from scratch. Okay. So I'm going to switch the image so you can see the Terra term. And now we're going to boot the system. And the first stage, bootloader is going to bring Linux onto the system. Okay. Another little shout out, if anyone is new to the stream, this is FPGA Zealot. We are talking about the Agilex 7. This is a Altera sponsored stream. We're going to look at doing basic board bring up and some live examples on the hardware. You can find this on YouTube, Twitch, or LinkedIn Live. The recording on YouTube and Twitch later if you want to go through it. Later weeks, we want to look at doing FPGA accelerators, mostly AI accelerators, on this Agilex 7 board, either through PCIe or the HPS. So look forward to those sponsored streams. And if you have any questions, you can post it in the LinkedIn, Twitch, or YouTube chat. I'll repeat it, and we can address any question. Okay. So now we're going to log in as root. Anything useful? I mean, we can cap the README real quick. The README mostly talks about the GPIO. What's the most useful thing? If we do GPIO detect. We can't really use this example because the hosted website already controls it. We'll just run GPIO detect real quick, and you can see the different interfaces. The GPIO info gives you the more. Okay. And then here's the FPGA LEDs. So we want to go to the website. So if we go info, or not info, I'm sorry, IP config, sorry, no, IF config. I'm not on Windows. Okay, 161. So we're just going to, I guess we'll just choose this window, 168.0.1. 161. Cool. Okay, so this website is being hosted on the development board, right? So this is purely on the Agilex 7 and hard processing system. Okay, so we have these LEDs. We can't really see it that well, but we zoom in to the LEDs right here. We can see there's some moving LEDs right there. Let's go ahead and stop the light show. Stop it. And let's turn all the LEDs. There's 4 LEDs. We turn them on. We can turn them off. Okay. Now we go back to the main thing so you can see this. And see if we can turn each LED on. And turn each LED off. And the only other thing, the example is talking about SSH. We do SSH and FFTP. So let's show those examples. The best place to do that is okay. So we can do SSH root at 192.168.0.161. We are now in the Agilex 7. We can do everything that we can do through the UART terminal. Another fun thing here, if we go see, make this a little bigger, right? We can do SFTP, and we can do LS, right? I'm sorry, LS, and we can see what's on our system, and we can do local LS and see what we have here, and we can be, hey, get that README. Look at that. Now we have the README locally. So we can do SFTP, and this file system will stay between boots. It's mounted from the SD card. So that's really useful. So we have basically, oh, you guys can't see this. Let me move this around. There we go. Oh, SFTP, getting the README, and you can see things. Great. So these are the examples that are shipped with the board. You need additional hardware for the QSFPs, the MXPs, and the FMCs to get it running. The USB-C, you probably get something working, but I do not see a working example of it. It'd be interesting to do PCIe over the USB-C, but yeah, I got no working examples. Okay, so let's bring up Cordis and do a very basic LED blink example. So we're going to create a new project. I swear this is faster without the streaming software. Okay, I'm going to pull up the, there we go. So we're going to create a whole new directory for this Agilex 7 bring up. And we're going to call this Blinky. And call it the Blinky project. Okay. Yes, we're going to create a new directory. Now we got to pick out our hardware. We're going to go to Agilex 7. And we're going to grab the specific version, which is going to be this guy right here. And there we go. We have what, close to 1 million ALMs, which I guess translates to LUTs, lots of memory, and 4 PCI high blocks, which is really good. We're going to hit next. We're going to add everything in directly and not worry about any of the synthesis and simulation tools, just to the default. Hit finish. Okay. We still need to set up the power bus. So the Agilex 7 and some other Agilex FPGAs has a unique feature where it actually controls its own power sequencing, which is really useful. But we need to make sure we have the correct component and the correct address and the correct I/O. So to do this, we go to Assignments, Device, or just in those window. We're going to go to Device and Pin Options. The first thing, we're going to go to the Configuration Pin Options. We're going to use SCL and SDA for the bus to the system. The SDA is going to be on IO 12. We're going to head and do config done on IO 16. And this is the basic system. You can look at the schematic and hopefully some examples of the design that show where this comes from. Okay, next, in power management, we're using the LTC. It's going to be at address 62. Okay. We now have a project that we can build a working bitstream, our SOF file. Okay, so we're going to add a new file. We're going to do a Verilog. We're going to copy over the file. So I'm just going to copy this over. I'm going to talk about it, why it builds. So here's our top level. Make a new one. This is going to be our simple process, the blink every second. Oh, that blinky.b. Yeah, it's 100. Next, we're going to add this GPIO system. So the LEDs are actually managed by the Max 10, the system Max 10. We'll show this in the schematic real quick. But let's get moving to that. So we're going to do another Verilog file. We're going to add this. This is going to be, you guys can't see anything, so there we go. This is going to be the SGPIO slave.b. Okay. One more thing, we're going to add the timing analysis. This is pretty basic. We're just going to have the main clock at 100 megahertz. Okay. Now we're going to make the top level. And we want to do some pin assignment. We want to finish analysis and synthesis to do pin assignment. So we'll let it build a little bit. And while it's doing that, we can talk about the Max 10 and are the LEDs. So these are the pins I'm talking about, the SGPIO pins. So if we go to page 50, we have the Max 10 system. And those GPIO pins are coming right down here. Yeah, right here, the FPGA sync, O, clock, and I. So that's where the Agilex 7 is talking to the Max 10, and the user LEDs, these 8 user LEDs are on your Max 10 and FPGA. So was it 19 we need to go to? No, we need to go here. So these are the pins we need to use. We have our basic clock, our reset, and then our GPIO bus to the Max 10. So we'll go ahead and assign this. Okay, we finished. So we're going to open up the pin planner, and maybe we can do this like side to side so we can see what's happening. Okay. Let's take, there we go. So you can see that. Okay, we're good. So first, we're going to get the clock, which is at 8E52. And for this, we're going to do a true differential clock, and that should automatically bring the N to P together, at least what I've read. Now let's get the reset. That's going to be AB53. Okay, now we're going to do the clock. No, the sync. This is going to be Y49. Clock is W48. I is E49. And we have U48. Close that. Now we need to go through the whole process again. So let's go ahead and hit the assembler. We do have a pre-built bit stream that we can look at. But let's go ahead and see if any questions from chat or comments from chat. We can talk a little bit while we let the tool do the synthesis and fitter, and then assembly, or assembler for the SOF file. Okay. Yeah. If you're joining the stream, welcome. This is FPGA Zealot. We're talking about the Agilex 7 FPGA, looking at the board bring up, and doing some live examples. Like right now, we're doing a blinky LED. This is sponsored by Altera. We hopefully can continue this in future sponsor streams to look at FPGA accelerators, focusing on Altera's FPGA AI solutions. You can watch this on LinkedIn. You can watch this on Twitch or YouTube. Feel free to talk in those chats. Share a little bit about your FPGA experience, and we can answer any questions you have. Okay, Monose123 is talking about Altera has had their own HLS for some years now, right? Yeah, so I wanted to look at the HLS. So my next example, if I have time, I'm thinking I'm going to do a little bit of HLS and do some Avalon Stream HLS manipulation. So if there is an HLS solution, I would love to do a quick example of it. If I have time in the coming weeks, I'll sneak it into one of the streams and we can look at how we can do a basic HLS example. Okay, we're making it to the fitter stage. And this is going to probably take a good few more minutes because this is a massive FPGA. If we had like a smaller Max 10 or Cyclone 5 or Cyclone 10, this would be a much easier process. It is quite a lot of computation to do place and routing for these larger FPGAs, even with simple designs. So we're probably going to sneak ahead of this step and use a pre-built bit stream to see how this system works. Okay, so we're going to hit auto detect. I might need to reboot the board. We'll see what happens. Okay. Oh, the HBS is on there. That's cool. Actually, I'm going to reboot the board real quick. Let me halt the processor. We're going to halt you. Not halt. Halt. Oh, you can't see. Halt. I'm going to halt it. As soon as it's finished, right now, we're going to turn it off. We're going to switch to JTAG. Bring it back up. Sorry. Walk around with my headphones on. Man, I should get wireless. I'd be much smarter for this situation. Okay, put that down. Hello, Bob. We're gonna say Yes, that'll leave this open. Okay. Now we're going to target this guy. We're going to change the programming file. And we're going to jump into... Sorry, I've been playing around a little too much. Okay, here we go. This is the blinky one we want to use. So Monose123, you're asking about AI. So the Agilex 7 is using a soft IP, I believe. There's no specific hardened block for AI. You're just utilizing the distributed DSP structure to be able to do AI. And the main point of these tools is usually to quantify and optimize your AI for the DSPs in the system. The Agilex 5 has convolutions built into the DSP. So it'd be really cool to do an AI, see how AI differs from the Agilex 7 to the Agilex 5, using kind of like the same utilization, see what the performance difference is. Bob, I don't know which evaluation board it is. I'll have to look it up later. Okay, so let's go ahead and program. That's still working on the place route. We'll go ahead and program this hardware. And we can see the blinking. Let's go ahead and make it full screen. So this is the most basic bit stream I think you can do on this FPGA. Just blinking all the LEDs once per second. I'm probably not going to post the source for this, but we'll see if I can find, I'll see if I can post this later. I don't have a good place to post it at the moment, but it's a very basic blinky LED. Feel free to pause the screen in the videos. Hopefully the resolution is good enough that you can read the source and copy and paste if you're using this hardware. Okay, so we're going to head and close the programmer. We're going to go ahead and stop the fitter. Probably going to take another 5 minutes. So we've done a blinky example. We're now going to look at doing a soft processor, the Neos 5G variant. So we're going to go ahead, open a new project. We'll try to go through this a little bit faster than last time. Okay. We were select 7, bring up, do what? Neos B top. Make sure the names I want underscore. Neos V top. Okay. Once we get this going, I'll show you where the user guide is. We're gonna do Agilex 7. The user guide, copy that again. Go ahead and finish. Then we're going to go up to devices and rechange those configuration pins. Okay. Power management, the LTC. 2. For future streams, we'll probably look at having the program projects all built up. I just want to go through these examples so you can follow through the GUI step by step. Sorry. Okay. You're right. Thank you. So we're setting up the NoSV project. And we've done the hardware. We've done the configuration, so you haven't missed anything. Sorry for not showing the screen. And you keep track of that better. So let's go ahead and set up the Neos V platform, and then we can talk a little bit. Okay. From here, we're going to go to Tools, and platform designer. It's going to pop up in the other window. I'll bring it over. Thank you, Bob, for catching the screen setup. Okay, so we have our Neos 5 top. We're going to create a new platform system. Great. Now we're going to walk through the process, getting a basic Neos 5 system going. I'm not using all the features. Hope we can talk more about other features later, but we're going to do a basic example. Okay, the first thing, we're going to set the clock to 100 megahertz. We're going to set the reset active low. And now we're going to add our processing system. Okay, we can't really see all this, can we? Okay, you all can see? That's good. We're going to do... I want to use the tightly coupled memories. I need to go get a working example to show you. Oh, custom instructions, it's cool. Okay, so we're just going to add this as is. We'll change it a little bit later, but we're going to add the processor. We're going to connect the clock and the reset. Now we're going to add some local memory. We're going to go to on-chip memory. And we're going to, let's see, how much do I want to add again? We're going to add 256 kilobytes, which is going to come to 262.144. Finish. Okay, next we need communication. For this, we're going to use the JTAG UART. We're just going to keep the basic configuration. We're going to do clocks, resets. Thank you. Thank you. Next, we're going to do the reset release, which is kind of like configuration done, like we have fully configured. We're going to pick the reset interface for this. And we're just going to, I guess, couple all the resets with this release. Okay. The on-chip memory, we want we're going to want instruction and data. For the JTAG, we're just going to connect the data bus. Okay, so everything is hooked up. Now we're going to assign the addresses. We'll go to System, assign base addresses, and we have the memory is going from 0 to 4, 0, 0, 0, right? So two things we're going to do on this system. You can see it. Yep. We're going to change this down a little bit. We're going to change the reset to be offset from the on-chip memory. Then we're going to add a peripheral region of 256, and this is going to be where the JTAG, the timer, and other stuff is. We don't want that to go through the cache. I don't know if this is automatic. I'm just doing this this is what I think should happen. I'm not sure what, if we don't do this, will happen, but I know this works. Okay, so I think we are good. So we're going to go ahead and save, and then generate the RTL for this. Okay, close. We're all good to go. Now we're going to generate the HDL. I'm just going to do all the default settings and hit generate. Okay. Well, we can take a moment and talk and answer any questions. Welcome to the stream. This is FPGA Zealot. We're talking about the Agilex 7 and currently going through some live examples. This is an Altera sponsored live stream. We hope to do more sponsored live streams so we can talk about Agilex 7 as an FPGA accelerator, specifically for Altera's FPGA AI solutions. It'd be interesting to take something done in PyTorch or something like that and bring it down to the Agilex 7 FPGA and see what performance per power we can achieve. You can watch this on LinkedIn, YouTube, or Twitch. If you want to watch the recording, Twitch and YouTube should have the recording afterwards. I'm not sure what LinkedIn does at the moment. Feel free to answer any question, ask any question in the chat. So, Guilherme, you asked about the ID stuff. What specifically? ID stuff for the NIAS. Trying to remember what ID stuff might be something important. Okay, I think we're good for now. Let's go ahead and close this. We have NIAS top platform system, whatever, as top level. Let's go ahead and do the synthesis so we get the pin placement going. And then we can do some software examples on the NIAS 5 processor. Okay. I don't know what that IP is at the moment, but if we go look at a question about the unique chip ID. So there's an example. Yeah, so we have a NIAS 5 processor tutorial. When generating this system, so we're going to build the hardware. These are the components that they talk about. So the processor, UART, on-chip memory, and the reset release. I don't know what the unique ID is, but I can look at that later and see what that is. Maybe this is being used at the moment. So on Twitch, we have a question from Heliosis, kind of talking about in-chip design development, either at like Apple or NXP or Infron. So I've mostly done FPGA. I haven't done like ASIC or custom silicon. There's definitely less rigorous testing and validation for FPGA designs than there are for ASIC designs. But I don't really have a good opinion about that. I've used kind of the embedded chips from some of these companies, but I haven't used it. I haven't, dug down into custom solutions in any of these more consumer chips. So I guess in my opinion, it'd be interesting to look at that. Most like more of the consumer chips, there's not public information to do low-level development or debug on it. But the embedded systems have seemed good and interesting. Okay. So let's do some pin placement, and then we can go and do some software. And then we'll throw in the STC file. Okay, so here we have JTAG signals. Those will be done automatically. So we don't need to do those. We just need the clock and the reset assigned. And we're going to use the same pins that we had here. So we're going to look at AE52. And we're going to do true differential reset, which right here is AB53. AB53. Okay, that's all we need to do there. Now we need to add some timing constraints, which I'll just throw into a quick file. I think it's clock. So we'll do that. And we'll just call this, let's make all the names super basic. Okay. And then we can go ahead and build this. We'll let this build the completion in the background, but we'll work on software and use a pre-built system to get this up and running. Okay, what do we need to do first? Okay, so first thing we need to do is go find this spring up. So we're going to create a software directory, and we're going to create a DSP folder. Okay, now we're going to open the Neos 5 Tickles console script from the Portis install. It's called the Neos 5 command shell. Okay, here we go. So here's the command shell. So we're going to, I don't want that big right here. That'd be good. So we're going ahead. What's it's going to be the 7 bring up CD Neos 5. Okay, this is the directory you want to do this at. So first thing is we're going to generate the BSP based upon our platform design. So with the JTAG UART and the on-chip memory, we're going to generate a BSP. So click enter. It's going to take a few minutes to kick off. Okay, so we have our HAL, which is a hardware extraction layer, and then we have our toolchain and CMake lists and linker. Get this all set up. Let's see if there's anything useful to look at. What's in this one? So it's kind of the basic functions. We have it for everything. But do we drivers? Probably more interesting. Okay, the JTAG UART. That's a system we have added. Okay, that's cool. Oh, this is probably one of the more interesting things, the reg file. So if you ever want to do low access register access to the JTAG UART, these are kind of the registers. And then we can follow the driver software and see what it's doing to read and write to the JTAG UART so we can get, hello world or whatever running. Okay, now we want an application. So come back here. We're going to create a new directory called app. And then we're going to copy in a hello C. I'll show it to you in a second. So we'll go here, copy in the hello C, and go ahead, see what we got. So this is the basic hello world. Every, so micro, milli, like 100 milliseconds? Or 100, no, this got to be more than that. It looks like every second, something like that. Okay. So to generate the make file for this, we're going to go Neos app, pick the BSP, the app directory, and the ELF file we want to produce. And it generates a CMake list. Okay. How are we doing on building? Okay, we're at the play stage. It's okay, we have other things we can work on. So next, let's pull up the RISC-V. Let me see. It's called the Ashling RISC-Free IDE for Intel. We're gonna pull up that install from our Portis Pro install, and then we're going to bring up the Neos software. Launch that. Okay, so Gila meme, you talked about the unique ID system is used for the HPS. So this example here, we're using the soft processor, not the HPS. I'm not exactly sure. I'm gonna have to look at the example design for the HPS to see what is happening, to see if that unique ID is used. The DE10 is a Cyclone or a Max FPGA, so it's probably slightly different on the HPS structure. But it'd be interesting to look at the generator. If we have time after stream, we can open up that platform and see what they do. Okay. Interesting. I feel like LinkedIn has a bit more of the latency. If you have any questions, you want like a quicker response, go to Twitch or YouTube. They seem to be pretty even on latency. Okay, Monose123, can you configure the Neos 5 to different presets and peripherals? I believe so. I've done the basic example, and my experience with other FPGA systems, you can do a lot more. So we'll look at doing DMA and some other basic bus examples with the Neos 5 in coming weeks to see how we can use that in these FPGA accelerators. Okay. Oh yeah, I'm annoying for this. Okay, Ashling, open. Okay. Make sure everyone can see well enough. The wrong one. We're gonna do this one right here. So first thing we're gonna do is go to the correct directory. Too many directories. Bad naming scheme. Okay, BSP. We're gonna add the BSP. Yeah. And this is just gonna add all the files that we already looked at. Anything useful in the settings. And it just looks like a JSON or XML-like file with this information. Okay. Okay, now let's add the application. We're going to do import another CMake project. We'll get the same little window. I think we should get the same little window. Did I miss it? I'll just do it this way. Weird. Okay. So we're going to go ahead and build the project. So this is going to build kind of our BSP and our application in the application project folder. So right now we're going to go through our hardware abstraction layer. And I don't think you're not required to use the hardware abstraction layer. This is RISC-V, and it's using some, you could probably look at a technical reference manual and be able to build your own super low-level BSP if you want to go that way. I don't consider the how like a required feature, but it's, if you're going to use the drivers provided by Altera, you're going to want to use the how BSP. There's also another version. I think it's for RTOS. Okay. So one thing to note, the program size is 80 kilobytes. So the how minimum size is like around 80 to 90 kilobytes. So you're doing like a max 10, Cyclone 5, Cyclone 10 with limited internal memory. You'll need to consider using external DDR and some like first stage bootloader if you want to use that memory, or finding a way to slim down the how BSP. Okay, let's go look at Quartus. We're still working on routing. That's okay. We got another bit stream we can look at. So next thing, we want to get the JTAG UART working. So we're going to go and add that. Okay, and this is just going to our Quartus install. And Quartus in 64. Scrolling down to JTAG terminal. I think it's something like that. Right here, JUART terminal. Then we're going to go look at the guide, programming the system. And we want to get this configuration. If you want to get more info, look at this guide. Basically walk you through everything. Apply that. Go ahead and close it. Okay. So we're not going to wait for this to finish, but we'll go ahead and load up another one. And we'll maybe take a quick chat break while we do that. If you're new, welcome to the stream. This is FPGA Zealot. We are looking at the Agilex 7 FPGA and doing some live examples. Currently looking at the soft processor in the S5 with the RISC-V architecture. This is a Altera sponsored stream. We are streaming on LinkedIn, YouTube, and Twitch. Feel free to use any of those chats to ask a question. YouTube and Twitch will be a little bit faster to answer this question. We hope to continue these sponsor streams to talk about FPGA acceleration of the Agilex 7, focusing on Altera's FPGA AI solutions. So that'll be in the coming weeks and coming months. But I think that'll be a lot of fun. If you have any questions or want to share your experience with the FPGA, soft processors, feel free to mention that in chat. Bob, you asked about how the Ashling is able to point to the BSP. I believe it's in the CMake list right here. So when we generate the CMake list, we target the BSP. So when we use the NEOS 5 shell and generated the application, the CMake file is the one that's going to target that BSP folder. Okay, let me grab that link for you. Okay, Kevin's got that link. Is there a way I can like that? Nope. Oh, there we go. Okay. Where were we? We were looking at the programmer. Okay, it's going to take a... That should probably finish pretty soon. Yeah, we'll just use the existing one. Nope. Go here. Change file. We want to go up. Okay, the template. Let's put that guy. Maybe we can look at using video compression within an FPGA, right? Using some of the video codecs. That's a really good solution for some data center FPGAs doing video codecs, compression, decompression, for being able to stream higher resolution video. Okay, we're gonna program this and then start up the application. Okay, so going back to Ashling, we're going to right click this and we're going to say run as Ashling hardware debugging. Hello, Elf. So now we have our run configuration. Now we have to go to debugger. It's got the debug board, JTAG, frequency. We auto scan because we programmed it. We're going to see the NEOS 5. You have multiple NEOS 5s and other things, you might be able to see multiple ones. It's going to be interesting to figure out which name is which. But right now we only have one in the system. So we'll hit fly, we'll hit run. Okay, it's going to run on the system. We're going to go ahead to our JTAG UART. Go ahead and run that. Okay, here we go. Now we want to do a new console window. I'm going to put that over here. Wish we could like do a dedicated one. Does it affect both? It affects both of them. I want to lock this window. Wish there's a way. Pin console. That one's gonna be pinned. Great. Okay, stop this. And hit. Okay. So if we stop it and then try to, oh, it's gonna rerun. I'm just curious. Do we need to restart the? Okay, it looks like we may have to restart. We have to restart this. I don't know. Weird. Okay, so we stop this one. We stop this one. We're gonna run the hello elf. Then we're gonna run the JTAG UART. Okay, now it's running. Okay, interesting. Okay, so we got the hello world working. We're gonna try doing a little bit some more fun applications, but that will be probably it for the Notes 5. Since Gilamim, we're gonna try to open up at the Linux system and maybe like poke at how the Linux system is working. So let's go ahead and do our next application. So we're gonna go here. We're going to make a drystone file, and we're gonna copy over our drystone. These are slightly modified from the official drystone. I'll show you basic change and some printout. And then we go and open this, and we're going to generate the drystone CMake file. Okay. Now let's go and import that. Using selected. There we go. Okay. So the only modification I really did to this, specific for this board, is we're using the NOS 5 timer. So we're going to use that built-in timer on the NOS 5 processor. We're going to use that built-in timer to time the whole drystone application, and then we'll talk about deep MIPS per megahertz. This is using a basic example in NEOS 5, so it's not going to give you the best performance. You'll need to look at the reference manual for the correct configuration to get the top performance. But one thing we want to do is we're going to go to, is it this one? Yeah, this file. So we're going to go right here. We're going to add an O3 flag to build the best performance. Go ahead and build this project. Okay. Let's go ahead and jump to reference manual right here. So this is for Fortis Pro 24.1. These are the reported max frequency, the sizes, and the DMIPS and the core mark. We'll see how close we get to the displayed information. We could put a lot of processors. I wonder if we do a processor array. How you would address each of those. Okay, so we built. Go ahead, kill the JTAG UART. Go down here, hello, kill that. Same thing, we're gonna right click this, run as, hardware debugging, the ELF file. Oh, I should show you the ELF file. We'll look at that in a second. Fly, run. Okay, jump to this. Okay, we'll let the dry stone execute. Let's go ahead and look at the hello world ELF file. So we go to hello elf.object dump. We can actually see what the binary is built out to. Okay, well, let's look at the dry stone real quick. We have all the correct outputs, which is great. The user time was this many cycles, and bringing that down, that's 1.2 DMIPS per megahertz at 100 megahertz. We can probably push the max frequency closer to 300, which would be really cool. But 1.2, we're pretty darn close. I might be truncating something somewhere, but that is a good number. But back to the object dump, we can see the different locations and memory. And when we do debug, we can actually follow what's happening. Should we try debug? Yeah, let's try debug. We didn't do debug. Okay, so let's demo that real quick. So hello here. We want to put a toggle a breakpoint there. Go ahead and kill this. Let's do some debug real quick. Kill that. Now we're going to want to debug hello.elf. Switch perspective. That's good. Okay, so it says we're on the looper. So now we're gonna bring up the JTAG UART. Put that, I guess, down here in the middle. Now we're gonna say run. Details. Oh, now we're doing the step. Sorry, step. Okay, we got printf 1, 2, 3. And now we're going to toggle the breakpoints and hit run. Okay. And then can we pause it? Oh, I'm back to doing timer real quick. Go back to looper. Here, let's toggle the breakpoint and run. Okay. Variables, breakpoints, anything else? Like the registers, purpose registers, floating point registers, DSRs. Oh, that's all. Okay, anything else useful at the moment? Okay, so there's a very basic debug example. Okay, so if you're new to the stream, we just kind of went through the bring up for the Agilex 7, some live examples. This is being hosted by or sponsored by Altera. We're gonna probably do a little more digging into the Linux design before we end the stream. You can watch us on LinkedIn, Twitch, or YouTube. LinkedIn looks to be having some trouble with the stream, but YouTube and Twitch are healthy. Okay, so let's just go open that design real quick. Close this. No. Okay, this did finish. It took 16 minutes to go through the whole design. That's about it, right? Okay, so let's go ahead and open the Linux example. Oh, we gotta subscribe. Thanks for subscribing. Okay, so we want to go here. No, not there. platform designer. So one HPF. No, right here. That's what I want to look at. So your question about the HPS and the unique ID, we can go and see what the Linux example is doing. Okay. So we have the hard processing system here. And it's mostly clocks, reset buses, interrupts. We'll see if that boots up and we can look at it. Yeah. That's external memory, the peripheral system, maybe the IDs in there. Pipeline, data, system ID right here. Okay, so we have the system ID peripheral. And this has a control slave. Okay. There is a system ID that way. So hopefully that answers your question. I mean, what? Okay, like double click this. Okay, cool. This is now full screen. Basic configurations. Box and reset. Box reset. IO. Okay. And then our UART, SD card, and Ethernet. USB. The USB works. Well, maybe we can do an example of that later. Okay. So I think that's about it for the stream today. I'll give you guys like 5 minutes to post any questions or comments for this session or the next session. For the future streams, we want to look at FPGA accelerators, kind of specifically for Altera's FPGA AI solution. So subscribe, follow me, Twitch, YouTube, Twitter, or X, LinkedIn, or whatever, and hopefully we'll have posts that will talk about the next stream that will come. If you want to watch a recording, YouTube and Twitch should have these recordings ready to review later. If you want to leave any comments on the YouTube afterwards, I'll try to address those when those come. But thank you for joining. Feel free to like, subscribe, follow, repost, share, whatever you want to do. Once again, thank you for Altera for sponsoring this. This has been a wonderful experience. I normally probably won't get my hands on this hardware, but hopefully we can help share how we can use the Agilex 7, which will carry over to the Agilex 5, and be able to show some really cool examples that can be used in industry, research, academia, and hobby. Well, thank you for watching. I don't see any new chats. LinkedIn is like, I don't know, 30 minutes behind? I don't know why LinkedIn is delayed so much. Okay, we'll have to figure that out. Thank you. It was fun. I hope we can explore more of the fancy features. PCIe, acceleration, the hard processing system. I hope we can learn more about that together. Thank you, and see you next time.